Hello, everybody. I'm delighted to have you at the first webinar from the Mocap Alliance, a cooperation of 4 different Vicon distributors in Europe. I will show you in some slides the different companies. Today's topic will be sports biomechanics, and we have 3 really nice presenters here and a special guest. You may know him. This is the program for today. Within 90 minutes, we will be able to listen to 3 really nice topics from Professor Nicola Petrone from Padova and from Eline Neichmeyer from Groningen, and also a really nice presenter from Switzerland, Maika Gross from our Olympic Center. We as a Mocap Alliance, it's 4 different distributors from Vicon. First, I would like to tell you about ProCare from the Netherlands. They are a Vicon partner since 1999 and covering the Benelux countries. Then we have GPM from Italy, also Vicon partner since 2012. With some nice people, as you can see here, covering Italy, Malta, Croatia, and the Balkans. Then our sister company from Sweden, Louise and Håkan, partner for a long time, actually, since 1994, covering the Nordic countries, as you can see. And finally, us, Prophysics, who are hosting this together with the other 3 partners. We are Vicon partner since 1996. Then I would like to hand over to Andy Ray, Head of Global Sales. He will say some words. Andy, please do so.
Indeed. Good afternoon, everyone. As normal, Eve, can you give me the thumbs up that we're all live and okay?
We are.
Perfect. Well, yes. Good afternoon, everyone. It's wonderful to be here. My name is Andy Ray. I'm Head of Global Sales for Vicon Motion Systems, celebrating my achieved 20 years at Vicon at the start of this year. And I'm super proud to have been invited by this Mocap Alliance of Prophysics, ProCare, GPEM. I think it's a wonderful innovation to do and put these things together and celebrating our community via these webinars. And I'm very excited to see the presentations today. I thought I would come in and provide a little bit of kind of insight to other like-minded community Vicon users and give you a little sneak introduction to some other work going on in the field. And I thought that would help us celebrate biomechanics. It would be wrong for the English guy not to start with cricket for sports biomechanics for the user community. And Loughborough University here are well celebrated in the world of sports biomechanics in research. Before I get into the cricket element, I think it's worth pointing out that 35 medals from the recent Paris Olympics can be routed back to Loughborough University. And so it's a really celebration of all types of sports and innovation there. But cricket has been obviously a long institution in the United Kingdom, and it is spreading around the world. And indeed, I know some players in Germany, of all places, for cricket. But what's also really kind of pleasing to see is the growth in the women's game. And indeed, Loughborough really at the forefront of that in looking at female biomechanics into this space and trying to see how we can really improve that world by way of motion capture. And they've done some great work that you can find via a case study online. And as you well know, motion capture, for its ability of speed and accuracy and repeatability, really is kind of letting them get into that type of study. The second type of biomechanics I thought I would bring to the fore is at University of Derby, where I think this is really intriguing to see the combined use of optical motion capture in IMUs, where they're able to kind of create that the template, the foundation within the lab, and the IMUs allow them to take it out the lab. And this is a really good insight to our solutions providing that capability to our clients. The third of these users outside of your community I thought I'd bring is Saucony, a very recent case study that we brought online for a running shoe manufacturer that really are doing amazing things for analyzing how athletes and their sponsored athletes are operating with their new shoes. And indeed, right up and down male, female, child, adult studies, you can find how they are using Vicon to solve these type of iterations of their product as they go forward. The last of the use cases I thought I'd highlight is in the world of golf and our client Ping. This is a more global entity going across Japan, United Kingdom, and United States, where they have multiple solutions around the world, allowing their elite athletes to come in and be assessed for the club swing with respect to their forward advancement of their coaching and becoming better players and having better use of the clubs. So they've really kind of utilizing Valkyrie in its most latest form of its high frame rate and indeed big windowing for golf swing analysis at those high frame rates. And of course, it's amazing to celebrate life sciences, but it would be remiss not to kind of comment of how motion capture does embrace multiple world of users, and it definitely keeps me entertained for 20 years at Vicon for being able to kind of see the world of life sciences, see the world of entertainment, engineering, and virtual reality, all utilizing the same technology together to do amazing things in this world. But of course, just because we create technology and those markets exist, it wouldn't really exist without you, our wonderful users. So we really are very thankful for all of you as our customers, and we look forward to the next 40 years. We celebrated last year our 40th anniversary. Here in this shot, you can see all our distributors coming to Oxford to celebrate the successes that we share together. And we wouldn't be here without the distributors that we have put on this event today of GPEM, ProPhysics, and ProCare. And I think we'll all acknowledge that their service and knowledge is really of such a high level of order that really ensures that our customers are really successful in using our products. So without that, that's just a quick whiz through. Thank you from me. You'll find me across all the normal URLs. And yeah, enjoy the rest of your webinar. Thank you so much.
Thank you, Andy. Very nice to have you here with us, and hope you stay another minute to listen to the presentations. Just some information. We have a Q&A chat. So whenever you have a question, please enter your questions there. We will ask or let the presenters know about your questions in the end of every presentation, and we have around 10 minutes to answer questions. Secondly, there will be a recording, so the whole webinar is recorded and will send out to you after today, probably on Monday. Then we will right on hop into the first presentation from Professor Petrone. If you like,
Hello.
You can start sharing your screen and introduce yourself. Thank you very much for being here.
Thank you, Yves. Can you hear me correctly?
Yes, we do.
Good afternoon, everybody. And I'm Nicola Petrone from Padova University. And I first would like to thank the organizers, Vicon and GPEN, for giving us the opportunity to present our experience. And I Just a few words about myself. I am a teacher of machine design, so I'm a mechanical engineer as a background, and I always been working in the structural and biomechanical behavior of equipments that are interfacing with the body. So we were studying bicycles, we were studying skiing, and recently we have been in collaboration with INAIL, that is the Italian government association that is supposed to cover the accidents and give the insurance and all the rehabilitation for the accidents in work. And they also have an attention to the rehabilitation to daily life through sports. So they're also covering and supporting the Paralympic activities. And that's why we work together since, I would say, 4 or 5 years now. And the track that I'm presenting, so the Olympia Smart Track that is being installed in Padova, particularly at Padova Pala Indoor, is the result of a common project that we call Olympia. If everything is okay, I can start with the presentation that is focused on this installation, and that's being used for running and jumping with a scientific approach, based, of course, in the motion on the motion capture integrated with ground reaction forces. So a full set of motion capture techniques. The project, as I told you, is supposed to cover and support the Italian, but not only Italian, Paralympic, but not only Paralympic athletes. So in any case, is focused on sprinting and long jumping, as recently in the past 2 or 3 also Olympics, we had a number of top athletes and elite athletes in sprinting and on jumping. And INAIL was searching for a partner, and they found us in Padova with some set of skills. And we worked together from the biomechanical and also the mechanical point of view. Let's say that our customers, in terms of project, are the most or the best Paralympic athletes that we have in Italy, ranging from long jump to sprint running, but also to triathlon. And our goal is more or less to support their best performance, so to possibly get to the medals, as it happened in Tokyo, and with the gold and the silver and the bronze, and also that we hopefully, and happen again, but not with all the 3 medals in Paris. So let's say that is focus on these top athletes. So the challenge is to support them in reaching their best performances, but in combination with an important parameter that is safety. So I was always impressed by this video. I hope you can see. It's just a training jump for a long jump from our Roberto La Barbera athletes. And if you look in detail, you see a piece of carbon flying out from the board that is due to this sudden failure at the takeoff. So the challenge is also ensuring the minimum weight, the maximum performance, but with a proper margin of safety for them, not only in the foot that is typically made by manufacturers, but mainly also at the socket, at the leg or the stump interface. Eventually, the challenge is also to promote sports. So through these champions, because they are really life champions, we would like also to help people that has been hit by disease or by amputation or other injuries to regain trust in life and sport activities, so promote the sports. Typically, we have medals, but also we have some other unplanned events. And these pictures or videos show what happened in Paris very recently, where our top player, Manu Maxwell, was eventually out from the 200-meter men final because of this slipping and falling. And in the very final of the 100-meter women, our best gold medalist, Ambra Sabatini, also fell, and she involved also two other and the second Italian runner. So sometimes unplanned events happen, and even going back to the analysis, it's not easy to interpret it and to avoid or to try to avoid these issues of safety and also of missed performance. You work 4 years for this moment, and then in a few seconds, everything runs out. So the project overview, very quickly. The ambition is to include in vivo tests from the track and the treadmill and perform the biomechanical analysis, but also to have attention to the device. So to have in vitro, we call in vitro tests on the feet, on the sockets, and some in silico, so numerical analysis for mechanical characterization of these devices. These two these two lines of research will get together for the improvement of performance and safety, and eventually, from a mechanical point of view, to the development of standard test methods and possibly innovative components. So it's not easy to measure what's happening in a final, in a track, in a long jump running. So the idea was, and the ambition was, to develop a track that could be a laboratory. And this was, again, faced by the project that INAIL and Padova and the Council of Padova City worked together to use the existing Pala Indoor 60 meters track with 8 lanes, and to extend to a 9th lane with instrumentation that we were deciding and also designing and choosing together with the GPEM and Vicon and MTI, as you will see. So the project ended up with the definition of a pit location that is typically at 35 meters from the start line. So when the athletes can reach the top speed, and the pit excavation and the casting of all the foundation, the application of this assembly box that was designed together with GPEN, and the application of force platforms in the floor. So 9 force platforms of 16, 19 dimensions, and 2 force platforms at the beginning, allowing for the application of the starting blocks, were then covered with the typical or the similar tartan surface and becoming a 9th lane, but this is a smart lane. So the smart lane can be used for performing the races and the sprints and also the starts. One of these platforms, even in precision, 2 of them can be also moved to the long jump track, and just before the pit, the long jump track is equipped by the force platform and can be measuring the force at the floor. Of course, this is a long work and some investment behind, but is worthy, and as well is an important investment, searching for 7 force platform with a full high and very high capacity loads in Z, and the 2 smaller ones in the block locations allow us to take, depending on the height and the step length, 3 or 4 ground reaction contact in a full speed run. So the structure, when it's used, is made also by a light lattice portal. This modular and portable structure is hosting our 10 Vicons that now became 12. We bought 2 more in the last few months, and some video cameras. They so far are just 2, but can also be added in other viewpoints, And then we also integrated or used together with the microgate optogate system. So on the right, you can see the smart track lane 9, and on the left, the long jumping lane. When the portal is moved by some rollers to the right position, or moved away from the 60-meter track for not being used. Vicon Valkyria are the motion capture systems, and we are here using the full speed of 240 frames per second. And the system is then integrating the amplification and the digital connections, and ends up with the acquisition system and the user for the running of the system. From the protocol or methodological point of view, we of course need to define athletes' marker set. So we define a marker set for the full body and for the unaffected limb and for the affected limb. The focus is on the trunk and the leg and the joint behavior, but also on the foot, deflection, and change of orientation. So you may understand how many markers are needed to cover in a proper way the lower leg, that is the main focus, the upper limbs and the trunk, and in the proper detail, the foot. So this is the view of the division of the system that can also be extended to some wearable systems. For instance, a load cell that is capturing the forces through this, you see, backpack, through the legs while you are running, even if you're not over the force platform. So you can measure the forces even if you are running in a circle or out of the track. In our period of usage of our smart track, we have been measuring as much as we could incompatibility with their training and their health state. Several athletes, you see, maybe you can recognize some champions, and more or less these were the type of output that we can collect. So we can have the full speed, the start from the blocks when the blocks are placed on the two smaller platforms, and the long jump when the fourth platform is placed at the table in front of the pit. So calibrating the system, as you know, capturing and the people running at 30, 33 kilometers per hour is challenging. And you don't see, or you may know that sometimes your markers are flying away. So if you have a good eyes, you can see some flying things. But nevertheless, we were so far collecting something like 220 runs, and these are very important for us to understand several aspects of the tuning and several aspects of the technique evaluation of our athletes. After the capture, of course, we need to do the data processing. So reconstruction in combination with ground reaction forces, as you see, can show the combination of the movement of the person and of the ground reaction forces collected at the force platforms. And we were also putting a lot of effort in this development of software that was able to combine the ground reaction forces to calculate the impulse at the ground floor, and studying the kinematic and the kinetic parameters throughout the joints of the person. So kinematically, analysis went through the collection of raw data, the labeling, and in our post-processing analysis, the introduction of coordinate systems that were especially challenging for the socket or the foot or the clamp, so the prosthetic affected part, and the calculation of typical biomechanical joint angles at the hip, knee, ankle, and or virtual particular joint that we could focus on. From a kinetic point of view, again, data from the raw data from force platforms needed some filtering, verification for absence of coupling, and calculation of all the components and the usage of these ground reaction forces and the inertial quantities for the inverse dynamics and the calculation of joint moments and joint powers. So the pipeline goes as typically happens due to the possibility of having several top speed or starting from the block quantities all together in the kinematic and the kinetic viewpoint. And as an example of outputs are, for example, the ability of changing and playing with different angles of pre-setting. So our athletes can run with different alignment angles that may range from something like 4 or 5 degrees to 15 degrees. And the attention was posed on the effect of different alignments on the trunk movement or the pelvis, but mostly in other joints. So on the left, in the unaffected side, and on the right, on the affected side. The ability or the difference can be very small, so you need particular care, but also the possibility of seeing these small differences is also, I would like to say, a merit of the precise and stable data acquisition system or motion capture system. So few changes can be felt by the athlete, but they can be measured only if you have a good precision and reliability of the system. So left, the unaffected side, for instance, the knee, you can recognize the physiological running. And on the right, you can recognize, for instance, a mechanical knee with a cylindrical joint that is only flexing. And there's no angle in the frontal, no angle in the transverse plane, whereas you can have some due to the calculation of angles or Cardan angles that has to be zero. And this is, again, another cross-validation of the quality of the post-processing and the kinematical analysis. From the ground reaction force point of view, then attention can be again posed on the small differences between the alignment in terms of vertical component or horizontal component of the ground reaction force that is changing from braking to neutral and to positive propulsion at the end of the stance. And in the prosthetic side, you see, or you can see, there are differences with respect to the sound size side, and more eventually, people expert in this field know that you push more with your prosthetic foot than with your normal foot. These quantities can be quantified and compared again in vertical and horizontal impulse. In particular, the horizontal is the focus when you search for the net positive or negative braking, typically coming from the the unaffected limb, and the positive impulse coming from the prosthetic side. So the total net balance is advantageous if you have a prosthetic foot that is able to give a positive pushing in the end of the stance that is giving a net positive impulse. But the differences are small. And again, it's a matter of measuring and asking the athletes to repeat the runs with the different alignments in the same intensity. So it's, again, a challenge to run the test. But you can see differences between two athletes, quite different in terms of shape and also intensity of the, you see, vertical force or horizontal force in these, for instance, same condition of alignment. When it goes to the jump is even more intense activity in the full takeoff, in the last takeoff instant. And here, motion capture is playing an important role in focusing where is the intensity, the direction, the rollover combination of the forces during the stance. So the focus was mainly on this takeoff action, and our output showed, as literature also have confirmed and already estimated, that you can, with the amputee foot, reach up to 6-7 times your body weight when you're taking off. And typically, you seems that you are braking, but you need that to go higher and longer in the trajectory of the flight. So the ground reaction force, the impulse are again the output of this effort. What's next? From the smart track, we would like to have information to run mechanical bench tests studying the feet in this tilting shank or tilting leg bench. And we would like to also study the feet and the socket with appropriate loads to compare with the real life and to reproduce and develop standard test method ensuring performance and safety to the athletes. And the next again is taking, for instance, in this case, able body data, but the future effort we're putting is in the athletes. So using OpenSim and musculoskeletal modeling to have an inside view of muscle and coordination and joint loading coming from the muscles. And focusing as well in the structural modeling of the feet and also of the socket. This is the example of the feet, where your track data and bench data eventually converge and have to validate each other in order to possibly play with new shapes or new materials for designing new components. And one of the most challenging as well is reproducing the full stance loading condition that you can appreciate here in the foot of Amber Sabatini, and reproduce the same in the slow motion, I would say, of course, dynamic, the same loading condition by moving the ground and the force during the rollover of the leg on the floor. Of course, I was presenting not only my work, so I would like and very happy to acknowledge all the big team that has been working with us during these years, in particular Samira Breban, that was supporting me also in the preparation of the presentation, and has been carrying on her PhD on these topics. So thanks to the athletes, thanks to INED for funding our research, and thanks to all of you for the attention during this presentation.
Thank you, Professor Petrone. We have time for some questions. Lisa is looking at the chat, at the Q&A question. Maybe I start with a question. Are you working with different producers of blades? Do you test like from Italy or outside of Italy also some products?
Yes, of course. You know that manufacturers of these special blades are not many, so they are very specialized, and typically the athletes are testing different brands and different models and different stiffness categories. So we have been testing and working on products that comes from Osur, Ottobock, and also from other companies that were proposing some specific prototypes. So we are mainly working in combination with athletes and trainers and INAIL in order to study the foot and which is the best foot that suits to the technique or the properties of the athletes. But of course, these data are very important also for manufacturers, because they, by the ground reaction force and the type of inclination of the loads, can design a loading cycle for their prototypes or their feet. So we are totally open to any collaboration or any request, and able to plan a special or using this data to support some design for in support the mostly the safety is the main, let's say, minimum requirement. And then performance is also a matter of tuning, alignment, and matching the force of the athlete with the stiffness and the response of the feet.
Mm. Other questions,
no
Lisa?
other question have arisen. No,
I
no
have
questions.
a second question, because this was a nice topic in our coffee break lately. We were thinking about Paralympic athletes compared to Olympic athletes. Which running distance you would say the Paralympic athletes really have an advantage with their prosthesis?
Can you repeat
which distance? So we thought 100-meter running, the start is maybe they are slower, so they won't catch up. And if it's like marathon with the artificial leg, let's say, there are also some disadvantages, but there must be for sure some distances where they have an advantage, right?
Oh, yes. Well, the fact that the foot is working more smoothly during the landing, reaching less higher peaks in vertical and producing more positive push forward is the reason why eventually they, the bilateral, for instance, have an advantage against the unilateral amputees, because they still have a natural limb that is working in the best way it could, but still is not working as the blade and the smoother propulsive energy return method that the blade has. So the discussion in also in the committees has been, as we know, trying to reduce the gap or the advantage and make the fair competition between the two, and shortening also the lag of the prosthetics has been one way to try to make this competition, or if the case, comparable. But eventually the Paralympic double amputee will for sure take over, and if the regulation are not stay like this and can not, let's say, even more strict, because the system is advantageous: less mass, more return, and more length during the contact and the push phase. The long jump as well, they always take off from the prosthetic foot because they can flex in dramatically this and receive at the right moment when taking off the energy. So I think it's still open at the discussion about the competition and the fairness of competition between the two. I hope that sometime this will become or be accepted, not only by, a communication or an event, but also by the philosophical point of view. I lost my leg, but I would like to compete in any case with you. But still, then with the medals, it will be some challenge, some challenge for sure.
Thank you. Lisa, good. No more questions. Thank you very much again for attending.
Thanks to you.
And
Thanks to you.
Hope to see you at the Congress. Maybe you
now
are
a question have arisen. Wait. So the question is, did you in the end find the problem with the athletes falling during running in the Paralympics? And then there's another one: since it seemed to be happen during a curve and you're now working on studying running in straight line to see less.
Yeah, thank you for the questions. I think these to pick up a critical phase. The critical phase for instance 200 meters is the curve. So Yves was asking which is where they're winning, where they're losing. In the curves, depending also on the side. If you're an external, you're better than in an internal, and the starting also, because the stiffness of the foot is tuned well for the full speed, but when you are starting the foot, the length of the foot and the amount of shortening that you can apply with your inertial force and muscular force is not enough to flex. So you have like a very long leg at the beginning that is still long, too long for you. So it's very easy that you step over. You really need to train a lot. We haven't understood very much the reason of the fault. Not much to do with the technical, but mostly to the coordination, of the athletes in what we reach out after this first analysis. And if you try to run with this knee, the knee is flexing. So it's not only you that you're keeping it straight. If you don't go properly backwards or extending your hip, the knee, in the case of transfemoral, flexes passively. So you need a lot of courage to run with that things and a lot of training, because if not, you just get a little distracted and then you may lose your coordination and then fall.
Okay, perfect. Thank you.
Thank you.
I wanted to say maybe we see each other at the ECSs in Rimini, right, this year?
Possibly, yes.
Nice.
Thank you.
Good. And
be
everybody
very nice.
else who is joining today will hopefully be there.
Possibly. Thanks.
Great. So say hello to Padova and hopefully see you in Rimini, right? Thank you very much.
I just would like to thank for again invitation and apologize with my colleagues, speakers, because I possibly have to leave in a few minutes for an exam, but I will go back to the recording and watch their interesting presentation. Thanks.
Perfect. Thank you.
Ciao.
Ciao. Then I would right away hand over to Eline Nijmeijer, and looking forward to the second presentation. Eline, are you there?
Yes, I am. Can you hear me?
Yes, we do.
Okay, and can you see the screen?
Yes, we do. Not in presentation mode yet, but
I will fix that.
ready.
It should be working right now.
It is.
Yep. Okay. Thank you.
Thank you.
Well, also from my side, thank you organizers for giving me the opportunity to present some work of what I'm doing. I'm currently a PhD candidate of the Department of Human Movement Sciences in Groningen, the Netherlands, which is focused on motor learning and reducing the risk of injuries, or basically, well, trying to reduce the risk by applying motor learning and using a lot of biomechanical analysis to see if we can basically reduce the risk of those injuries. Why ACL injuries? Well, we see that currently the rate of injuries is still increasing, especially in the youth soccer girls. And we see a lot of those injuries appear during cutting and pivoting sports such as soccer, basketball, but also American football and that kind of stuff, but especially the Netherlands, a lot of soccer. For example, here you see that Vivianne Miedema is rupturing her ACL injury. And those injuries go along with a lot of negative consequences, such as, well, needing a surgery, a lot of time to recover, to coming back to sport, hopefully at the same level as you was before getting the injury. And if you are below 20 years old, especially for the females, we see up to a 6 times higher risk of getting another ACL injury, even at the same leg or the contralateral leg. So what our idea and our goal is to reduce the risk of getting such an injury. And, well, luckily spoken, a lot of those injuries occur without direct contact, which means that it is, well, basically due to the combination of several not that favorite moments that occur within the lower body, such as an extended knee, knee valgus, and also that the tibia is rotated externally. And if we then look at the model that was proposed by Bittencourt colleagues about getting injuries, you see a lot of components that we cannot change, like you have a several age, you're on several level of anxiety. But what we also see is that those injuries are related to several biomechanical factors. And because those injuries mostly occur without any contact, we do think that by changing those biomechanical factors, you should be able to reduce the risk of getting such an injury. So that's where we are working on, and that's also where motor learning comes into place, because we see that a lot of current prevention programs do not work that efficient enough. They exist of a lot of relatively simple exercises with the intention that there is a transfer to the real training or game. So from going from a predictable environment to an unpredictable environment. However, according to us and also the literature, this transfer is not going that well. Possibly also because there are low motivation rates by both coaches and athletes about those programs. They don't like it, it's not sport specific, etc. And therefore we think that by changing or getting new ideas about how we can use motor learning to optimize those prevention programs, we should be able to, for example, use implicit learning to learn better, retain your movement skills, and therefore also reducing the risk of such injuries. How do we do that? Well, we make use of several products of Vicon, for example, the Vicon View cameras, but also the infrared cameras. And we combine that with force plates to get the full kinetics. Here, okay, I thought it was one slide further. What we currently use is the Vicon plug-and-play lower body model combined with some markers from the upper body, but for us the focus is on the lower body, and to make it that feasible enough, we only place the markers on the lower body combined with some of the upper body, and then we combine that to the model that you also saw by the previous presenter. This is an overview of the lab that we currently use. It's basically also a gym where PE students get their lessons, so we always have to build a lab up and break it down afterwards, which is a disadvantage. But on the other side, one of the advantages is that we can make use of the whole room. So we make it sport specific by adding balls, boxes. We also can do, for example, research with volleyball players or basketball players. We are not doing that at the moment, but we are able to. In green, I highlighted the cameras and the force plates. Maybe you see that those cameras are not the newest one. That's true because it is a picture from some years ago. Sorry for that, but it was one of the pictures that I had with a nice overview, I would say, of the cameras, and not all the cameras are visible because some are still on the wall behind the scope of the lens. Here you can see one of the movements that we are trying to investigate. We call it side-step cutting maneuvers and then unanticipated ones. So the participant has to react on someone else instead of make it predictable by just saying, okay, make a sprint and then go 45 degrees to the left. We always include, as we call it, a sports buddy to do the exercise together with, which makes it unpredictable, also more fun to do, but also just more unpredictable, more like a training or a game scenario. And during the past years, we wanted to investigate if the movements that participants made in our lab are comparable to the ones that are currently done on the field. Because a lot of training, but also screening is still done in the lab for a lot of sports. And the question was, okay, is that still ecological valid enough to do, or should we move to the field? And of course, both have their advantages and disadvantages. But our first exploration was, okay, are there differences in the movement patterns itself? I will skip this one because, mainly it's already shown by the former presenter. So going back to the differences, what we did was we made clusters based on the movement patterns of the participants in the lab from the top to bottom, cluster 1, cluster 2, and cluster 3, going from low risk to high risk in terms of ACL injury mechanisms. And then we compared that with how those people behave on the field. So for on the field, we used IMUs because, of course, we cannot move the Vicon cameras together with the force plates outside. Here you see from left to right again low to high risk, which came primarily due to changes in knee AB or AD duction moments and also the rotational moments. So there were no big changes in the flexion moments between the three clusters, but we saw it mostly in the frontal and in the longitudinal plane. From this point on, we made our own conclusion that, well, if we increase the environmental complexity, then differences may partly disappear if we translate those clusters to the field. So what we did, we made the clusters based on the lab 1, 2, and 3, and then we collected data from the field, and then we compared cluster 1 with 2, 1 with 3, and 2 with 3 to see if the differences were still there. And indeed, there were still differences in the way that the girls with the high flexion and the less abduction moments in the lab, which we classified as low risk, move kind of the same on the field. So those who are classified in the lab as safe were safe on the field as well. So that was fine. But those that showed less knee flexion in the lab showed that also in the field. So based on the knee flexion, you can make the same conclusion either from lab or field data. But the ones that showed high knee abduction in the lab, which is highly recognized as one of the variables prone to getting an ACL injury, were much better on field. So when the complexity increased, those were kind of, I will not say definitely safe enough on field, but they showed much better movement patterns on field, which may lead to the conclusion, okay, not always your definition or your conclusion based on lab says enough about how you do it on field. So that is one of the studies that we performed recently, combining the Vicon stuff with IMUs as well. But it also leads to one of the studies that we are currently doing, which is called movement optimization through video instructions and feedback with individualized training in soccer. It is still in the lab. We are able to make the transfer to the field as well. But the nice thing about the lab is that we can combine directly the data that we got from Vicon via MATLAB to scores that the girls will receive during their training session. So not afterwards or 1 week later, but during the training session. So what we do, it is an intervention study which use video instruction and feedback. Girls come to the lab for 4 weeks in a row individually and perform single leg jumping and landing, double leg jumping and landing, and side step cutting tasks. We currently work with the girls of the female academy of the local academy here in Groningen, called FC Groningen. And they receive feedback, as I already said, which is based on the video footage, a score based on kinetics, which comes directly from Vicon, from the Vicon cameras combined with the force plates, and also an implicit learning tip to even help the girls further to improve. So those 3 components I will say a little bit more about. So first, they will see themselves performing the exercise whenever they want. They can request feedback, and then they see a video from the sagittal plane. And then also from the posterior view, we played it not at normal speed, but a little bit slower, because those movements are currently performing quite fast. So then it's quite hard to see what am I doing. So we played a little bit slower. That's one component. The second one is that based on the data that we get after every trial, we calculate a knee load and an ankle load and combine it together. And then the girls receive a score. And for them, the challenge is to lower the score. So they do not know where the score comes from perfectly. The only thing they know is, okay, I get a score, the lower to 0, the better. We correct that for body mass to make the scores even comparable between athletes. And they are trying to reduce it, reduce the score. And of course, they know that we are busy with doing stuff related to injury prevention, but they don't know if they have to bend their knee much more or lower or whatsoever. So it's kind of a self-organizing process. And then we combine the video with the score and a verbal cue from our side to even improve more on. For example, as you can see here with pictures, most of the cues are related to an external focus or implicit learning. So not too much words and also not related to the body itself, but more to, well, the goal of the action. So what do you want to achieve? And then, well, we hope that by combining those motor learning principles with, amongst other, the video instruction and the video feedback, that we can make improvements in the factors of which we know that they are related to ACL injuries, especially to the non-contact ones, to help athletes improve their performance and therefore also reducing the risk of injuries, and also the other way around, because we always say, okay, if you are injured, you cannot train, so therefore you can also not well, become better. So we are working both on, well, the injury risk reduction part, but also performance optimization. If you want to know more about this study, please ask me later. The first things, well, the first results that we got are already published, but that was not with the feedback part, but only with the video instruction, which is already interesting, I would say. But the most interesting part is, are the girls able to catch up all the feedback that we give them? And we are currently in the late phase of the data collection. So no results for that yet, but they will be there soon, hopefully. Then again, well, you cannot do research alone, and those are the main persons that are helping me along the way, getting more knowledge, perform better, but also, well, getting hopefully even better prevention programs to help athletes in the future to perform better. That was it. Then I would like to thank you for your attention, and if there are any questions, I'm happy to answer them.
Perfect. Thank you very much. Lisa, are there questions?
Yes, two questions have arisen. So the first one is, how do they estimate knee kinematics on the field?
How do we? Well, based on the IMU, so that are accelerometers, you can calculate position of the sensors, and based on the position of the sensors, you can calculate the angles. So then you have the kinematics. We are also trying to predict or estimate the kinetics, but we are doing that by making use of machine learning and first get kinetics and kinematics in the lab. And then we train the model to predict the kinetics based on the kinematics, knowing what the kinetics should be, because we have them from the lab. And then we translate that to the field data to also predict the kinetics over there. But that is just a prediction. But the kinematics can be collected quite easily based on the IMUs.
Okay, thank you. So the other question is more like a double question. So could the difference between laboratory and field setting in knee abduction measurements be influenced by psychological factors? For instance, could the awareness of having to step onto a force plate unconditionally alter the movement part in itself?
Yeah, good question. I think I cannot say with 100% certainty that that is the case or isn't, because indeed those differences are there. Yeah, the girls know that on the field they don't have to make the movements at a specific place, because we can measure them basically anywhere. In the lab, they do know, but one of the things that we use to reduce those influences is that the force plate is embedded in the floor already, so they don't have to jump on it specifically. And one of the other things is that they basically focus a lot on the person that is running in front of her. And then it doesn't matter if she stepped off a bit, then we do it again. So yeah, it may have an influence, but I will not say that it is the influence on the results directly.
Okay, perfect. No more questions there. Thank you.
I would have another question. Are you trying to apply what you did for football players to other sports? Because ACL injury, of course, is also happening a lot in other change of direction sports, right?
Yeah. Well, right now for my PhD project, the focus is on soccer and a bit on basketball as well. Hopefully, yeah, in the future I would like to apply it to many other sports, but for my PhD project at the moment, this is enough to hopefully graduate.
What do you do with basketball? Is it the same, or what did you change?
It is a bit of the same, but for that study we only use the IMUs because then they don't have to make indeed the movement on the force plate itself. But in another study we still used Viken. So there we used the force plates and we investigated what the effect is of having the autonomy about the timing of feedback. So one group received their autonomy about the timing of feedback and they can request feedback whenever they wanted, and the other group was matched. So they just received feedback after the 5th, the 7th, and the 10th trial, for example. And then we figured out that if you have the autonomy about the feedback, you performed better, not during the training session, but 1 week later. So 1 week later, they came back, did the same exercises without any instruction or feedback. And at that point, the group with autonomy performed better in a way that they reduced, the risk factors related to ACL injury risk. So that was a nice achievement, I would say.
Nice.
So
Other
another
questions?
question. Yes, another one. So the question is, do they use a model with the IMU sensors to estimate the knee kinematics, or is it a relative orientation between the sensors?
Sorry, what was the first part of the question?
Is there a model used with IMUs to estimate the knee kinematics?
Yeah, it is. We use the IMUs of Xsense, and they have their own model indeed to calculate the kinematics. So we use that at the moment.
Perfect. So there are no other questions right now.
So thank you again.
Thank you.
Of course, people can reach out to you bilaterally to discuss things. And will you be at Rimini?
Probably not decided yet.
Okay, perfect. Dankjewel, and see you around. And I hop over to Micah, so we can stay in time. Maybe we will a little bit late for around 5 minutes, but the last topic today is also a really interesting one. It's about sprint analysis with markerless tracking. It's a pretty new sprint track, but Micah will tell us a little bit more about it. Thank you very much. We do not hear you yet.
Now you do?
We do.
All right. Can you see my opening slide here?
Yes. Yes.
Okay.
We do.
All right. Well, I'm glad to present the third part of this webinar from Switzerland. Talking about our sprint lab and what we intend to do there and what we've achieved so far. So just a little bit of background. I'm Micah Gross. I work at the Swiss Institute of Sport in Mocklingen. So it's a center with sports medicine, sports science support for a lot of the national federations. Actually, very many different sports come through our labs and our institute for support and for assistance. So so I've been here for 10 years. I actually did my education more in the exercise physiology, but have really transferred a lot to the biomechanics since I've been working in Mockling. And so one of the big achievements at our institute was this new lab. So I continue. This is our sprint lab, or our sprint tunnel, you might say, that opened just about a year ago. So it's 90 meters long, and which is enough space for a fast sprinter to do a full 60-meter sprint, and with enough space to slow down. So some of the instrumentation, just to let you know what's going on. We have actually the opto jump are going the full 60 meters, and then we have an area of 10 meters instrumented with force plates. So we have a system based on it's integrated into Vicon's Nexus software. So we have actually 8 FLIR cameras and a couple others for the calibration. And then we have the Kistler's 3-dimensional force plates covering a full 10 meters of the track. So we're getting up 4 to 5 steps at high speed. We also have an instrumented start block. You can see in the picture at the right. So we've got these 3D data also flowing into over the lock sync box into the Nexus ecosystem, and timing gates as well. The opto jump is the only one that's not integrated into the Vicon system. The rest is all synchronized. Just something also to the floor. The floor is actually like an indoor surface. It's not a tartan surface because we decided as a compromise, because we're working with a lot of different sports, not only track and field, for this type of floor, but the track athletes are also able to run with their spikes here, and they're used to it enough if they do indoor competitions. So our applications for this lab is to mostly, was either some of the sports we're working with, not only track and field, but also other sports that are accelerations and short sprints are important. Soccer, ice hockey, actually not sprinting, but they do sprint tests. Handball, floorball, bobsledders also do some sprint tests, and actually BMX racers are doing some stuff on their bikes. So our main focus, as you can see, is for providing support for the athletes in the form of performance testing. Research is an obvious second area to use this lab for, but it's not our primary focus in the development and application of the lab. And then what would really be nice to achieve is if we get to the point where we're able to have athletes training in the lab and have some sort of direct feedback from the measurement systems. So when I talk about performance testing, what we're most interested in doing is applying or assessing the transfer of some of the lab tests we've been doing for years. So we have really well established tests for maximal and explosive strength, and also reactive strength in the lab, doing vertical jumps. You can see the picture doing some isometric squat strength, also some vertical jump tests. And what's been lacking is sort of the transfer of these abilities to the sport itself. So you can imagine the explosive strength in a vertical jump is a great ability to have for a sprint start, but you have to also be able to transfer it to the start blocks and to the track. So this is the sort of the step further up on this cascade of abilities that we're hoping to achieve with our lab, with the start blocks, with the force plates, and also the motion capture for just looking at the technical abilities to apply their force in the sports setting. The same is true for sort of the reactive strength that we're measuring in the lab with reactive drop jumps. Of course, that's really important at the high speed sprint. So this ability to get a really high vertical impulse to keep the center of mass above ground with incredibly short contact times. So the ability that we measure in the lab, we're now able to measure something comparable on the track with the forces, and also get some qualitative analysis from the motion capture. What I'd like to say is, in a setting like this, if this is our goal for using it in performance testing, even hopefully at some point as direct feedback training, there's a marker-based system really is out of the question because of the time requirement for the markers, and just while it's not a huge interference, it is a bit disturbing, and so we decided to give it a try with the marker-less system and the Thea algorithm that's built into Nexus, in order to get some at least good 3D qualitative images to provide some feedback and to get some to do some qualitative analysis, and within research setting maybe definitely look into doing some quantitative analyses. So some of the things we've achieved so far is, and we're working on, is sort of, at the one hand, these are some pictures of the ground reaction forces at near or at maximal speed, and we're just beginning to analyze these and hopefully be able to provide some feedback. You can see these are 3 different athletes. The 2 of them are specialists in sprint on the track, and one of them is an athlete from a different sport. And what you can see is different forms of the curve, with this initial peak in the picture at the left. There's literature suggesting that this is probably coming from the hip extensors slamming the foot into the ground in order to get this vertical impulse going as quick as possible with really short contact times, and you see that that's lacking from this athlete here. Of course, yeah. So and you can see at the one on the right, the peak is actually during the braking phase. The absolute resultant force peak is during the braking phase, whereas with the specialist, it's closer, or even in the closer to the propulsive phase. So these are things that we're looking to use as some sort of feedback. Another parameter that we're using from the force plates are just quantifying the impulse. So this is at or near max speed. So the actual net impulse are just enough to overcome the drag forces, but you can see the net forces are the height of the bars here, but the lines are representing the braking and the propulsive impulse. So these are actually resulting in a net impulse that's shown by the bar, but how far that the 2 points go from 0 or from the net impulse is also a factor that we're looking into to explore the efficiency of these steps at maximal speed. Down below is actually the same run. The vertical impulse is represented with the bars, and the black dot represents the required vertical impulse to counteract gravity, which is working during the contact and flight phases. So another interesting application that came about, we had actually some reporters come into the lab and do a short report of our lab, and then they came to me with several questions about sprint, often citing some of the popular research. And there had been a study out there that had been cited a lot in sort of the popular science media of analysis of 100-meter sprint, particularly the world record of Usain Bolt. And there they had published that 92% of the energy in the sprint was going to overcome drag forces. And they asked me if this was realistic, and I thought, well, I don't know, but I can calculate it. So I did some calculations. So these were, yeah, so these are like in detail calculations. These require the trajectory and the speed of the center of mass. So these are coming from the markerless tracking combined with the 3D ground reaction forces. So what I did was calculate the power and actually the cumulative work done by the ground reaction force, by the drag force estimated by the speed and body size, and also of gravity. But that is minimal here at the maximal speed phase, so you can see what's happening actually. It's enough to look at the bottom graph. You see what's the cumulative work done by the in the negative direction. So it's the forces resisting the velocity of the center of mass, and by far the greatest one is actually the braking phase of the contacts, the ground contacts themselves. Of course, it's necessary to have a braking phase, because otherwise there's no chance to generate the vertical impulse needed to keep the center of mass above ground. But the drag force itself was around 20%. So there were a few blatant methodological errors in the paper that they had cited, and so these were like interesting findings and calculations that we were able to do. Actually, the same thing for the start phase. There, of course, the gravity is playing a larger role, but the overall resistance is a lot less. Gravity, because the center of mass is elevating during the first few steps. So the percents are different, but the overall resistance is much smaller. One of the projects we've begun in a pilot phase and are working on, actually, we've gathered quite a bit of data and are in the phase of sort of deciding what we want to analyze, is comparing sprints with assistance. So sprint starts with different resistances. We're using the 1080 sprint device for that, and also flying high-speed sprints. As you can see the video here, but this one's in slow-mo. She's got the resistance coming from the belt, and here's a impressive video, although it's not playing quite as fast as as real time would have it. But yeah, doing assisted sprints in our lab. So it's great that we have the ability for them to get up to speed with assistance and then run over these 10 meters of force plates and through the motion capture volume. So this is a project that's planned, but don't have much to report about it other than that so far. So. Another project we've been able to do with our unique setting is some measurements with the change of direction. So you can see actually here, these are the velocity, the time plots from changes of direction starting from different distances. So they're coming either from 15 back here off the chart, off the graph, from around 10 or from 5 meters. And doing a 180-degree change of direction, as you can see here. And we were able to quantify stepwise the horizontal, all the forces, but we're showing here the horizontal forces and impulses. And this was it's cool that we're able to do that in such a large area and gather all the forces and have the trajectories of the center of mass, because it allows you to make the change of direction not at a precise point, but they have an area of 2 meters or so where they can do it, so it makes it a little bit more natural. Yeah. So we used here, this was for identifying the steps, it was quite of a challenge, but we were able to use the markerless tracking of the feet to identify the steps in the force data. It's obviously not very challenging if only one foot is on the ground at a time, like in these steps up here. But at the point where they turn around and there's steps that are overlapping, so left and right at the same time, it was a bit of a challenge to develop an algorithm for identifying the force coming from each foot independently. So you can see that one side is green, one side is red, and at this point they overlap. So that was really valuable to have the tracking of the feet on the force plates, and to combine that with the center of pressure data from the force plate system in order to identify force coming from both legs independently. So one last application that we've done some data analysis collection in addition to the sprint tests that we already do. So they have the BMX riders in the sprint lab. Before we weren't able to do that indoors in a control setting, but we have them doing accelerations from zero. That's also a test sort of to evaluate the transfer of their strength and their explosive strength to their sport. So additional of getting the 3D images could help us to also to do some qualitative, at least qualitative technical analysis combined with the acceleration data which we're getting from the Blue Trident IMUs on the crank arms, and combine that with some measurements of the force we're getting from the pedals to do some additional assessment of technique and force application transferring from the lab. So yeah, that's sort of a sum up of 1 year in our sprint lab. Yeah, thanks for listening, especially thanks to Eve and the team from ProPhysics, because they've been involved the whole time helping us get things set up. And with a setting like this, there's some initial challenges to be overcome, and we appreciate their help. And yeah, I thank also my colleagues and our working in the lab and helping to get these things up and running. So you can see this is a picture showing that there's a lot ahead, and yeah, there's but it's already been an interesting experience, and hopefully a good opportunity to provide some helpful information for our athletes, and maybe some opportunities for collaboration with other scientists and from the field.
Thank you, Micah. There may be some questions, right?
Yes, there one
Nostra.
question is there. So have you investigated how accurate the markerless system is obtaining 3D kinematics compared to the marker-based system, or do you have any clue about the accuracy?
We have not done that. We don't actually have the ability to do. We don't have any marker-based cameras in this lab. We do have a marker-based system in another room, but we don't have them in the same place as of yet. There have been some studies doing that, but at much slower speeds than we are doing with our athletes. So definitely that's an open question that needs to be answered, and that's why I sort of tended to emphasize that the system is going to be helpful for doing qualitative analyses. As far as quantitative, that's sort of an open question, because the validity compared with the marker-based system needs to be assessed at these high sprint speeds, especially. But yeah, we haven't had the opportunity to do that yet.
Okay, thank you. No more questions there.
I have a question for you, Micah. As we heard the presentation of Professor Petrone in Padova, they are studying a lot about prosthesis. Is this also the plan in your lab? Because of course, also in Switzerland there are Paralympic athletes. I know there's the center in Nottwil where they do some things. Will there be a collaboration? Is there already something you know about what you will do, or is this the future?
It's an open question. We have had sprinters from our Paralympic Federation in Mocklingen. We have done tests with them in the strength lab before, and we did actually some sprint tests before we had the new sprint lab opened. So I'm not sure what's planned. That the situation in the past was a sprinter, a female who was in the military sports program, and so definitely it would be a possibility in the future, but I'm not sure if there's actually concrete plans for the immediate future or not. Not that I know of. Yeah.
And other sports you will have studies on? I mean, we saw already a lot within a year, right? But I know you have a lot of different athletes. I mean, it's for me, it would be interesting to see, or we all know, ice hockey player, a football player, and a sprinter. They are totally different in kinematics if it comes to sprint, right?
Yep. Right.
Yeah, whether it helps or not, right? But will you do some other sports in your tunnel, or will it be mostly the professional sprinters actually?
Yeah, well, the most athletes that'll come through the sprint lab will actually be team sport players, just because there's a lot more of them than there are sprint specialists. But we're working on the lab with according to the demands of the specialists. So at the peak of the pyramid are the true sprinters, and we're trying to do our best to accommodate their needs, and that'll certainly cover the needs, the less the smaller needs of the team sports. Of course, there are opportunities to do some unique things, like with the BMX riders is one example. I'm sure there are other opportunities that are not coming to mind right now, but yeah.
So there's another question. So first of all, compliments, and it's very impressive. And the question is, can you repeat which surface is on the force platforms and which force platforms, Kistler?
Yeah, let me back up to the picture showing the best. Yeah, so actually just at the beginning, right? Yeah, this one. So you can see this is the force plate zone. You've got the overlay of the video here. So it's the Kistler plates embedded in the ground. There's also, it's very similar to the pictures that the first presenter showed. So there's a hole built into the concrete, and the plates are then anchored below the floor. And then there's a floating piece of this PU floor over the force plate. So it's one piece cut out with this 10 meters by 60 centimeters wide, so that it's basically this piece of flooring is floating with a very small gap to the floor around it. Did that answer the question?
Yes, and there was the last part is it a Kistler one?
Yes. So they're Kistler force plates.
Great.
So those were fairly easy to integrate with the Vicon system. We had some also before we had this lab. We had 2 mobile force plates from Kistler which we're using, so we'd always been pretty happy with them.
Great, and 2 more questions. So, are you using Nexus/ProCalc to calculate the kinetic data based on the tire segments and force plate data?
We're using Nexus, yeah, for the capturing, of course, and ProCalc I've really only been using for the representation of the 3D image. because you get this skeleton overlay. And the other data processing is being, well, you've got the ProCalc processes also integrated into Nexus for calculating the kinematics of the body segments. Yeah, but otherwise analysis of force data and of the trajectories and the connect data that just have been done outside of Nexus with custom Python programs, actually.
Perfect, thank you. And the last one is, did you compare marker-based system and IMU in sprinting?
No, we haven't done any marker-based sprinting, as we've said. Shorts, we have a different lab in the building that's not as long, but it's wider. It's more like a small gymnasium with our marker-based system. So we'd actually have maybe an opportunity to do that there, but it's not on the radar. But
I think the question was about IMUs too, Micah. If you compared IMUs to markerless, because you have the blue trident,
okay.
right?
Right. No, we haven't actually done any sprints with the blue tridents yet. I've used them in particular for the BMX because you get a nice rotation signal from the gyroscope, and you put it on the crank, and you get a really nice, high resolution signal of the acceleration. Other than that, we've done some experiments with the IMUs, but no applications in sprinting so far.
Perfect. No other questions have arisen.
Good. We are almost in time. So thank you, Mike. I don't know if somebody of your team will be in Rimini, but I think this will be a really nice gathering of people that were here this year. We'll come to an end of this webinar. So thanks again to all three presenters. It was really interesting. There were interesting questions. And there was a question while preparing this webinar if we as a Mocap Alliance will have other webinars. Probably we do. Probably not about sports biomechanics right now. Maybe there are 1 or 2 webinars each year. Sometimes maybe about robotics, sometimes ground truth systems, other topics. But for sure, we're coming back to sports biomechanics. During the time. So I think this was a success. I really enjoyed listening and watching what you were presenting. So thank you again. And also thank you to the participants and to Andy Ray, who had a short talk, also to the community. So we'll be back with other topics and hope to see you soon. Stay healthy, enjoy the winter, and yes, speak soon. See you around. Thank you, and have a good afternoon. Bye-bye.
Thanks, Eve.
Thank you. Bye. Speak to you soon.
Bye. Bye,
Thanks.
everyone.